All right, so welcome to day 4. It's the end of our first week, and today we're going to be looking at the overview of the baking process. So once we've mixed everything, our products are going to go into the oven, and there's a lot that happens to a baked product when it goes in the oven. So during baking, heat is slowly conducted from the outside in, and heat transforms the batter or dough from a foam that traps air bubbles to a porous sponge that does not. The term sponge is used whether it has a springy, spongy texture or not, just because it has air bubbles in it. Those air bubbles are what add tenderness and make a product more edible, make it much more enjoyable to eat. So let's start off with the baking process. So crumb or grain of a baked good consists of air cells surrounded by porous cell walls. You can see it in the photograph here, all the little cells. All of them are porous, they contain air, but they also contain moisture, and that moisture will migrate through the product as it's baked. Everything is starting to change when it gets into a warm environment. All those ingredients are going to start playing in concert, very much like an orchestra. You've got all these different instruments, you've got all these different players, and they all have a part to play. And if one is missing, it's noticeable. So baking involves at least 11 events. It's really complex. They oftentimes are happening at the same time, and they do influence each other. So that means that water, for example, is moistening, but it's also dissolving other things. It is soaking into other things, and it's starting to get to the boiling point and creating steam, which is affecting everything. So everything is happening at the same time. Many would never occur at room temperature, so heat is required. And several have no upper limit. That means that as long as they're baking in the oven, as long as they keep going, these processes will not stop. Good examples of this are like protein coagulating. That will not stop until an item is in the oven long enough to catch fire and turn to ash. It will always continue coagulating the protein. Gelatinization of starches. Starches will continue to gelatinize, which means they soak up water at a rapid rate, and they'll keep doing that and keep trying to soak up more water until there's no water left. And again, at that point, it gets hot enough, there's no water left, it catches fire and turns into ash. And then evaporation of gases, that keeps going as well. Evaporation of both gases as in water vapor, but also other gases like carbon dioxide, and other straight gases that are in there. They will continue to evaporate out of the baked good as long as heat is still there. So the first thing that really starts happening at a very low temperature is fats start to melt. Those fats are usually the hard fats like butter and lard and shortening. They're going to start melting between 90 and 130 degrees. What this does is it starts increasing the volume because the item starts to get softer when the fats that were hard are now turning into liquids. And the rise will start to happen to products because the air that is trapped inside is starting to expand. So if we have a product where we choose to use fats that melt at a higher temperature, you're going to get more volume. A good example of this is shortening. Shortening melts at a higher temperature than butter, and oftentimes when you use shortening, you will get a little bit better volume than you will with butter. This increases tenderness, and the melted fats coat all the structure builders. So the sooner the fats melt, often the more tenderness we get. So a good example of that would be, for example, when we use oil in pie pastry dough instead of using butter or shortening. If you have oil in there immediately, the fat is already melted. It's already in a liquid state, so it's going to create more tenderness. But it also makes it more delicate. Because it's because the fat is starting to melt as well, it will start to thin the batters and doughs. Things like high-fat cookie dough, most cookie doughs are high in fat, they will start to spread. And that's because there's a point at which in the baking process that things that have fat trapped in them, especially hard fat, they will start to melt and turn into a liquid, and the whole batter starts to turn into something of a liquid. It's a very vulnerable time for baked products because for that about 10 minutes or so in the oven, those items are very, very delicate. So then, after the fats are melting, the gases that are trapped inside start to form and expand. Now, I say form because sometimes the gases are brand new because they're being created by baking soda or the baking powder, or extra gases are being created by yeast that is reaching a higher temperature. So the three most important gases are like atmospheric air, steam, and carbon dioxide. This starts to happen as soon as the temperature starts to rise, but it continues until about 170 degrees Fahrenheit. At that point, most of the gases are starting to escape. This results in increased volume. So we'll see that in breads, for example. When you put a loaf of bread in a loaf of dough in the oven, it will increase in size, about double in size. We call that oven spring. That oven spring occurs usually in breads in the first 5 to 10 minutes, and we see a dramatic increase in size. And it increases tenderness because the gases make the cell walls very, very thin, and that makes them easier to bite through, which makes them feel more tender in the mouth. Now, of course, then, after all that's happened, microorganisms start dying. At about 135 degrees, microorganisms will start to die. This includes yeast. So if you're using yeast in a product, your yeast will really have a full die-off by about 138 degrees Fahrenheit. That means that any yeast that's at the outside of a loaf of bread, for example, near the outside, they're going to die first. Then the ones toward the middle will die a little bit later because the heat takes a little while to get to the center. But that also kills molds and bacteria and viruses. So if there's any chance whatsoever of foodborne pathogens, they're going to start dying at about this temperature. So it depends on the microorganism. Some are more resistant than others, but this stops fermentation. It also makes the food more safe because any bacteria that happens to be there will be killed. So things like salmonella, hepatitis, E. coli, other foodborne pathogens, they will get killed in the process as well. This makes baked products generally very safe to eat after baking because they've come out of a hot environment and that has killed all the bacteria that could be harmful to us. Then the sugar starts to dissolve. Now, some of these overlap. You're going to notice that sugar starts dissolving as soon as heat starts to be applied. So even as low as 110 degrees, we see sugar that has been dissolved in liquids will start to dissolve, not just because of being dissolved in liquid, but the heat will start to melt the sugar as well. So this results in moistening, tenderizing, and eventually browning, because eventually sugars get hot enough where they start to caramelize. And of course, sugars help sweeten an item as well. So the sugar is going to start turning into a liquid both through dissolving and through melting, and help to make the product more tender. It'll help thin the batters and doughs. And sugar tends to grab onto moisture. All sugars are called hygroscopic, in that they love water. So they'll grab onto the water and hold onto them, which is a good thing for most baked products because that means we have a good moist product. Most products that have good moisture usually have high sugar content as well. So other things that dissolve during baking include acid salts. So acid salts are added to baking powder, and those acid salts, when they turn to liquid, they start reacting with baking soda that is also included in baking powder, thereby creating a chemical reaction, and we get carbon dioxide from that. That creates more air bubbles, more cell walls that get stretched and get thin, and of course increases tenderness. So the sugar has a lot of roles to play. It's doing a lot of things at the same time. Finally, eggs. Eggs, when they reach about 140 to 160 degrees, they start to coagulate. And we see that when we cook eggs on a pan. Eggs change color, they start to turn solid. Basically, that is the protein coagulating, And basically the egg proteins denature and bond, forming a network of stretched out clusters of egg protein. The heat dries out and stiffens those proteins, and they help to form the structure of your product. In some cases, the eggs are the only structure builder. A good example of that would be like an angel food cake, where eggs are probably about 90% of the structure builder in an angel food cake. Flour plays very little role. They're very little in the way of other dryers. Mostly, angel food cakes mostly made out of egg foam and sugar. There's a little bit of flour, but mostly it's egg foam and sugar. So that is an example of an item where eggs really play a primary role, but it helps to form that rigid structure that helps to sets the final shape and helps the baked product survive after baking and be able to hold up its shape against gravity. So then we get starches. Now, starches are kind of mysterious in that they are just little granules that are naturally occur in plants, and we'll often see them in the form of cornstarch, for example, but there are starches in wheat and all grains. Gelatinizing of starches means that starches at a certain temperature will start to grab onto water and swell. Now, we see that if you ever used cornstarch or ever used flour to thicken something like a gravy, it will go from being very liquid to being very thick when it reaches a certain temperature. What that is basically the starch is soaking up the liquid and increasing in size dramatically. What this results in is thickening of a batter or dough. It does help to form something of a rigid structure that helps to set the final size of the baked product. So starches work in concert with other things like proteins to help hold the shape and help give set the final size for your baked product. Now, the only thing about starches, in order for it to work, you've got to have heat, but you also have to have water. Starches by themselves will not gelatinize without water. So once they have water, though, they will grab onto that water and absorb it and hold on to it. That's a good thing. Now, of course, after baking, starches start to release their water. And that's something that's referred to as a process called, instead of gelatinization, it's called retrogradation. Retrogradation is where starches start to release their water. And when they release too much water, we usually refer to that item as being stale. So staling is the process of basically starches retrograding off some of their excess water. Now, then we start getting to the point where gases start evaporating. At about 160 degrees, rigid cell walls rupture from pressure of expanding gases, and gases start to escape. This results in a dry crust on the outside of your baked product. In this case, it's still a white crust, so it hasn't caramelized yet. The sugars that are naturally in the product, whether they be added sugars or whether they be natural sugars, they haven't started caramelizing just yet. Now, when gases evaporate, that also means we're going to have a weight loss. Usually about 10 to 12% of the water will form water vapor and gas and just disappear. It also means some loss of aroma in the process. But that doesn't mean that baked products don't smell good. They do still smell good. There's still plenty of aroma where that came from. But that process of releasing some of the gases is actually a good thing. We want a certain amount of loss of moisture in order to balance out that baked product to make it something that's not too wet, not too soggy. Finally, we get to caramelization and the Maillard browning. This begins at 300 degrees Fahrenheit. So we're going to see this first occur on the very outside of a baked product. So on the very outer crust, it reaches 300 degrees in an oven first, before the center does. So that's why we get a crust on the outside and we don't get the browning on the inside, because we usually stop the baking process before it gets too brown. Once it reaches 300, though, sugars that are naturally occurring in the product and added sugars will start to brown. And then the sugars will start to bond with proteins. When they bond with proteins, then we get an even deeper brown color, and that's called Maillard browning. That was discovered by Francois Maillard. He was a French chemist, And he discovered that you have to have the proteins together with sugars in order to make it happen. He wasn't a baker. I'm sure then he had a friend or somebody who was a baker, and they did some experimentation and found out that if you go a little bit further beyond regular caramelization, you can end up with a deeper and more significant browning. So what does that result in? Brown color, but great flavors as well. After all, a baked product that's light in color, light yellow, it really doesn't have a lot of flavor. It's the browning that gives you flavor. So never be afraid of a product getting brown. Browning equals flavor, and that's a good thing. So there's a point at which then we get up a little higher in temperature, 160 to 180 degrees, especially when we get near 180. Enzymes start to be deactivated. Below this temperature, rising oven temperatures increase enzyme activity. They get really excited, partly because they know they're going to die, and they start to do all kinds of reactions. We have amylase enzymes, which eat up starches, and we have protease enzymes that eat up proteins. In the case of the proteins, these are biological catalysts that actually speed up the chemical reactions. They're denatured by heat, so amylase enzymes are a good example. They're very naturally occurring in almost all grains and all plants, and they can cause a lot of good things to happen. They help increase tenderness, they help increase flavor, and they help to release acids into your product to help increase the flavor balance. So, next step, step 10, changes in nutrients. Obviously, when we bake or we cook something, we're changing the nutrients in a product. So the proteins, fats, carbohydrates, vitamins, minerals, they all get changed. Some of them are deactivated, and that's just the nature of cooking our food. So there's going to be a certain amount of change in our nutritional balance in food. So proteins and starches, for example, start becoming more digestible. The destruction of certain vitamins, like vitamin C and thiamine, they start to break down. Thiamine's in the vitamin B family. And that's just the nature of cooking food. Step 11, the pectins start breaking down. If you have fruit in a product, like a fruit pie, you'll notice that the fruit starts to break down. Berries start to crack and break open. Fruits start to get soft. And what's happening is, in between the plant cells, you have these little things called pectins. And pectins are what hold the cells together. When the pectins break down, they will start releasing the cells, and the fruit starts to release juice. That's a good thing. That's a good thing, because what happens is the juice starts to mix with starches that are naturally occurring, and we get thickening of the fruit juice, and thereby a pie that has nice thickened fruit juice in it, good moisture, and a good texture. Okay, so when it comes to cooling, once we pull things out of the oven, carryover cooking continues cooking the product until the baked good reaches room temperature. When you first remove something from the oven, it starts to stale immediately. The good thing is that staling isn't something that becomes unpleasant for a couple of days. But changes occurring during cooling and continue during storage. So this is why a lot of baked goods need to be wrapped in order to reduce the amount of staling and reduce the amount of retrogradation that's happening in the starches. Many changes result in firmed baked goods as they cool. They start to firm up, and you'll notice that they cut easier, they cut more cleanly when they're finally cooled. It is best to cool products down to about 100 degrees or below before slicing, getting them down to room temperature. You'll get better results when it comes to portioning and cutting your items If you try to cut, let's say, brownies when they're first out of the oven, you'll usually tear them and make a mess. If you wait, let them firm up or chill them, they will cut much better. So 8 main changes are happening when you're cooling. Gases start to contract because gases expand when they're heated, so they start to contract when they are cooled. And we can see some weaker structures like soufflés will start to actually collapse. Fats start to resolidify. Items that had turned to liquids will start turning back into solids. Now, there is a risk that things could become hard and waxy when they get cool. Those are items oftentimes that we prefer to reheat. So things like danishes, we also like donuts when they're warm, things that have high amounts of fat in them that could become hard and waxy when they start to get solid again. Sugars start to recrystallize. Sugars that had melted and had dissolved in water will now start recrystallizing, and that can create crunch in the crust. It can create a wonderful texture, and that's just part of having sugars in your baked products. And then starch molecules begin to bond and solidify, and they start to retrograde. This is the major cause of staling, but as I say, most of the time we don't notice it getting stale until it has reached a certain point. When it reaches a certain point, we just say, oh yeah, that's just not good anymore, that's just stale. Well, it's just part of the process, and that helps us determine our shelf life. How long will a product last until it becomes stale to a point where it's unpleasant to eat? And of course, proteins start to bond and solidify. That helps contribute to staling. Moisture is redistributed within the crumbs, so you'll find that moisture that seemed rather moist in the center, well, what will happen is as it cools, it will start to become more even. The sugars will, the liquids will start to spread out and get everything more evenly moist. The moisture moves from the moist crumb to the dry crust, so you'll find that crispiness in the crust can become tough and rubbery, but oftentimes just not really rubbery, but much more just a little softer and a little easier to bite through. Flavors do start to evaporate or become trapped by the starches. That's why when you briefly reheat some items, some baked products, you just briefly reheat them in a toaster oven, they suddenly seem to come back to life. And that's partly because what you're doing is you're forcing those starches to release those aromas, those flavors, and release some of their moisture. And they seem to have better texture that way. So today in the lab, we're going to be preparing a pound cake. And based on the concepts we've learned about this week, we'll take the time to watch these 11 steps of baking in action as our pound cakes transition from a batter to a finished product. You'll see in this picture that this picture is a perfect example of what I'm describing. Pay particular attention to the final stages of baking as the top of your pound cake splits open, the center changes from liquid to solid, and the Maillard browning creeps from the outer crust down into the valley of the top split. It's at this point, when you see that browning creeping into the valley, goes from the mountains to the valley, that's when you know your pound cake is done. If you try to pull it out earlier, while the valley and in the crack on the top is still yellow, that means it's not done. It'll still be too moist, it'll be unevenly baked, and it won't have nearly the quality you're looking for. So shortly after baking, release the pound cake from the loaf pan and start the process of cooling. You'll see where starches will retrograde off some moisture. You may even see some steam coming off of it. Proteins will start to firm, and the crisp crust start to soften from the release of excess moisture in the form of steam. So the whole pound cake will start to get even better a couple hours after it's been baked. And I find when I make a pound cake, it's even better the next day. Flavors seem to migrate more evenly, moisture migrates more evenly, and you'll see that the product just gets even better and better. So today's lab isn't really about filling out a lab form, but more preparing for watching these events taking place. We can use our oven that has the glass doors on it, so you can actually go back to the oven and watch different stages occurring as they happen, and you'll be able to go back and take a look, Walk away for a few minutes, come back, and you'll see your pound cake will look totally different when you come back. But do pay attention to that browning down in the valley. That will tell you that your pound cake is very close to being finished. Anyway, we'll see you in the lab and see you tomorrow.